third session of this course. In the previous sessions, we introduced modal logic and we become familiar with the basic notions of modal logic, and also we introduced cryptic semantics of modal logic. As we said, cryptic semantics has introduced after topological semantics, but because it provides a better intuition for but because it provides a better intuition for learning about the basic definition, and also it provides some useful techniques for proving some results in topological semantics. We start by learning cryptic semantics. Let's have a brief review of that. As you may remember, a cryptic frame is a pair of W and R, where W is a non-empty set and R is a binary relation over W. And a cryptic model is a triple W, R, and V, where V is a valuation function from the set of propositional variables to the subset of W. This function assigns to each propositional variables a set of states in W. And we have the satisfaction relation, which says that, for example, in W, the formula P is true if and only if P is in V of W is in V of P. For negation, we have that M and W satisfies the negation of phi if and only if phi is not true in W. For disjunction, we have that phi or psi is true if and only if at least one of them is true. And for modal operators, we have that the amount of phi is true in W if and only if there is at least one state V which is accessible from W and in V phi is true. And since the box operator is the dual of diamond operator, we have that box of V is true in W if and only for all V. If V is accessible from W, then phi is true in V. After that, we study topological semantics. As we said, topological semantics is introduced by McKinsey and Tarski. They proposed two kinds of topological interpretation for modal operator. One is to consider the modal operator diamond as closure operator, and the one is that to consider the modal operator diamond as the derived-set operator. In some literature, they are called as c-semantics and d-semantics. C-semantics is for considering the closure operator, and d-semantics for considering the derived-set operator. We study by c-semantics. As we said, in c-semantics, the satisfaction relation is defined in this way. For propositional variables, the negation and disjunction, we have the same definition. But for box or diamond, we have a new definition. Our model is in this way. We have a topological space with evaluation, and we have that diamond of phi is true in point X if and only if X is in closure of phi. And by this notation, I mean the set of all point Y where phi is true in Y. So equivalently, the amount of phi is true in x if and only if for any open set u in tau, if x is in u, then there exists some point y in u such that phi is true in y. Again, for a box operator, as a dual operator of diamond, we have that box of phi is true in x if and only if x is in interior of phi, which means that there exists at least one open set u into such that x is in u, and for all y, if y is in u, for all y in u, phi is true in y. So the diamond is interpreted as closure operator and box interpreted as interior operator. We see some examples which are definable in more topological properties which are definable in modal language, and some properties which are not definable in modal language. Also, we introduce topological semantics, and we see that here we have a version of Van-Bentem characterization theorem, which shows that modal logic is a fragment of first-order language, which is invariant under bisimulation. Also, we saw that for any Kripke frame or Kripke model M, we can see F as a topological space. We can assign an offset topology to F, which means that we can see, for example, F is equal to X and R. Now we can define a model M, which is X and tau R and V, where tau of R is the set of all subsets of X, such that for any point X, if X is in U and X is related to some point Y, then Y is in U, which means that U is closed under accessibility relation R. This topology is called as offset topology. And we saw that if F is transitive and reflexive, then the space X and tau of R is an Alexandrov space. An Alexandrov space is a topological space where the set of open sets is closed under arbitrary intersections. Or in other words, each point has a least open neighborhood. Also, we saw that if X and tau is an Alexandrov space, then we can define a specialization relation over that, which is defined as follows. And X and R of 2 R of 2 is defined as follows. X is related to Y if and only if X is in the closure of Y. Then in is a reflexive transitive frame. So there is a one-to-one correspondence between reflexive and transitive frames, and also Alexandrov spaces. And in this case, we have that in M and X as a cryptic model, phi is true if and only if in M and X as a topological model, phi is true. Then we show that S4 is sound and complete with respect to the class of all topological spaces. Recall that by soundness and completeness, we mean that first recall that S4 was the system K plus the axiom which says that P then diamond of P, and the axiom says that diamond of P then diamond of P. These axioms characterize the class of reflexive frames in the creepy semantics, and this axiom characterizes the class of transitive frames in the creepy semantics. And soundness and completeness are theorems which says that for any logic L and class of model C, if phi is provable in L, phi is provable in F if and only if phi is valid in C. In this case, we say that the logic L is sound and complete with respect to the class C. To prove this theorem, we can construct a topological model, which is called the canonical topological model, or we can use the results from Kripke frames. We proved this theorem, we proved it by using the result from Kripke semantic. We showed that since S4 is complete with respect to reflexive and transitive frame, we can show that S4 is complete with respect to class of topological spaces. Moreover, we have a theorem by McKinsey and Tarski which shows that S4 is also complete with respect to any dense in itself metrizable space, or S4 is complete as a special case of the second part. We can show that S4 is complete with respect to real line or with respect to rational line. The original McKinsey-Tarski theorem has another condition which our space X is separable, but after that Raziova and Sikorsky showed that we can drop this condition and have the theorem in this case. At that time, Kripke semantic had not introduced, so they used techniques from they used properties from metrizable space and topological space, and also Raziova and Sikorsky theorem used the axiom of choice. Today, I am going to give a idea and a sketch of proof of completeness of S4 with respect to real line, but in a new technique, not the one that used by McKinsey-Tarski or by Raziova or Sikorsky. For that, I'm using these references. For completeness of S4 with respect to real line, there are at least three different proofs. One is the version of the McKinsey theorem. I mean that the proof that they proposed. There are two other ones. I'm going to use the one that is proposed in this paper. Also, in this one, they mimic the proof that proposed in this paper to provide a version of McKinsey-Tarski theorem for any density self-metrizable spaces. So I think it's a good idea to be familiar with the idea of proving this theorem from this paper. Okay, if there is any question, please ask, otherwise we can continue. You can ask your questions in the chat bar. Yes. Because of the restriction of time, I can't give the complete details of the proof, but I try to give the ideas and make it clear how they prove this. Okay. To prove the completeness, I have to show that if phi is not a proof, is not a theorem of S4, then there exists some topological model M and a point X in M such that phi is not true in this point. So our theorem which we want to show that is S4 is complete with respect to the real line R. So I have to show that for any phi which is not a theorem of S4, there exists some topological model. And in here, since we are going to prove the theorem for R, we have to show that there is a valuation on R and at least one point in R such that phi is false in that point. So suppose that phi is not a theorem of S4. From the Kripke semantics, we know that S4 is complete with respect to any reflexive and transitive frames. And also we said that S4 has the finite model property, which means that any formula which is satisfiable has a finite model. By these results, we can conclude that if phi is not a theorem of S4, there is a finite reflexive transitive frame F such that phi is not true in that frame. So if phi is not a theorem of S4, there is some frame F which is finite, reflexive, and transitive, and there exists some model M based on this frame and a point W in F such that Y is not true in that point. We can assume that F is generated by X because in the Kripke structures, as you saw, the satisfaction of formula is just related to the points that are accessible from this point. And also we said that we can define the generated subframe, a generated subframe of, for example, the point W contains all points which are accessible from W. So I can assume that this frame F is generated by a point W, and we can call it a rooted frame, which means that it has a root. We call it, for example, R, and all other points are accessible from F. Especially in this case, because we have the transitivity, we can say that all points are accessible from F in one step. Given any topological space X, if we want to prove the general case of McKinsey and Tarski theorem, I mean, we want to prove for any density self-materializable space, or in this case for R, the key point of the proof is that we have to transfer each such finite frame to a subset of X. I mean that we have to define a function F from X to F, which is a bounded morphism or interior map in topological space. We called it interior map. And if you can remember that interior map is a function which is open and continuous, and if we have a surjective interior map, then the validity is preserved, which means that if some formula is valid in here, then it's valid in here. Or in other words, if some formula is satisfiable in here, then it's satisfiable in here. So if phi is not true in this point, means that the negation of phi is satisfiable in F, so the negation of phi is satisfiable in here. So it means that we can find a model based on X which refutes phi. So the main challenge in the proof is to construct such a function. It's not very easy to construct this function. And I'm going to try to explain how we can define such a function for any finite reflexive transitive frame. Okay. But as soon as we can define such a function, then as I explained, we can prove our theorem. So the main part is to show how to construct such a function. Let's start by a very easy example. Suppose that our frame is a two-fork frame, which means that it's a frame in this case. We have 3 points, and it's the root of our frame, and we have 2 successors of that. Then to define a function f from R to this f, I can send 0 to the point R, and the set of all negative points to, for example, one of these points, for W1 and W2, to, for example, W1, and all point in the positive part to W2. I write it in this way. I mean that for any, it's better to write it in this form. Or to W1 if x in this interval, and W2 if x is in this interval. So in this case, we can define f very easy. But how about a complicated frame? If we have a frame which has a greater depth with more successors. We do this in some steps. First, we show that we can define f for any tree with depth 2. So the first step is to show that that we can define for any n tree of depth 2. Then we extend it by induction to the tree, to any finite tree. Then we consider the case that our frame contains clusters, which means that our frame is not necessarily a tree. And for example, we have such condition in our frame. By cluster, I mean that the set of points where are, for example, if W is related to V, then V is related to W. I'll define it in a couple of minutes. And for this case, we consider again some cluster which has a simpler figure, or the one which is more complicated. So the first step is to show that we can define a function f for any entry of depth 2. Our method is to send the contour set. For example, I have some frame in this form. It's a root of our tree, and our tree is of depth 2. We want to send the contour set to this set, and then to the children of this root, we assign the contour set of appropriate interval of module 2. So first, recall the definition of constructing a contour set from any open interval. Assume that I is any open interval, or we can also assume that it's a closed interval in R, which means that A is less than B, and A and B are in R. So in step 1 of constructing the contour set from the open interval I, we have to take out some open one open interval in the middle of that. So we take this open interval, which is a plus b minus a over 3 and a plus 2 to the b minus a over 3. So we take out this interval, and the remaining closed intervals we call them J11 and J21. We can see that J11 is equal to a to a plus b minus a to the 3, and J21 is equal to a plus 2 3 to c. In the second step, we take out some open intervals from these closed sets. So we take out the open intervals I12, which is equal to a plus b minus a to 3 to the power 2 and a plus 2 to the b minus a to 3 to the power 2 and I22, which is a plus 7 to b minus a 2 and a plus a to b minus a to 3 to the power 2. We take out these open intervals and named the remaining closed one by J12 to J42. In general, in a step M, we have to take out some open intervals. The open intervals I1M to I to the M are taken out, and the closed intervals j1m to j2 to the power m remain. So it's a review of how we construct a contour set from any open interval. We continue this method, and then we consider the union of these remaining closed set. Now we can show our first lemma. We want to show that T, at the first step, we want to show that if T is any tree of depth 2, then it's a interior image of some open interval. T is an interior image of I. So in this case, I want to show that any such tree of depth 2 with n successors is an interior image of any some open interval in R. We define a function f which we call it f of I and t from I to t as follows. F of I of t is defined as, let's call these points t1, t2 to tn, to tn. We send x to the point t ka if x is in the open taken out interval IPM, where p is from 1 to 2 to the power m minus 1 and m is congruous with k mod of n. And we send x to R otherwise. So for any x, if x is in the contour set, we send it to the R, or if it's in the some open intervals which we take it out, we send it to one of these t with respect to in which step we take out the open that x is its member. I think I don't have enough time to go to the details, but we can show that FIT is a surjective interior map. And by interior, I mean open and continuous. Now, by this theorem, I can show that every finite tree of branching n is an interior image of I. At the first step, we define a function for a tree of depth 2. Now I want to show the I want to say that we can define a function for any finite tree of any depth. We will prove it by using the induction and the previous lemma. Suppose that T is a finite tree of branching n without loss of generality. We can assume that the depth of T is d plus 1, where d is equal or greater than 2. Then we can represent our tree as follows. I can represent it as this shape. Call this part T of P, and the whole one is T. Where T1 to Tn are elements of T of depth 2. These are tree of depth 2, and it's the remain part of the whole tree T. And Td and T of T is the subtree of T of all elements of T of depth equal or bigger than 2. Now I'm going to use our induction and the previous lemma. Note that for each k in the set 1 to m, the opposite topology over R over Tk is isomorphic to the tree of depths 2. Each of them is a tree of depths 2. Of depths 2 and branching n. So by induction, and TD, T of D is the tree of depths D and branching n. We assume that D is equal or bigger than 2 and T is has a depth of D plus 1. So each of them is of depth 2 and this part is of depth D. So by induction, hypothesis, there is an onto map onto interior. From I to T D. So by induction hypothesis, we can define a function from I to this part of T. And by the previous lemma, we know that for each of these three, I can have an appropriate function. Also, by previous lemma, there exists an onto interior map from I into each RTK. Now can put these functions together. Then we have an appropriate function. we don't have enough time to say how we define these functions and how we put them together. You can see the details in the reference, but as I said, I just want to mention the idea of proof and the sketch of proof. So in this way, we can find a function for any tree of depth n. It's the step 2 of our proof. Now we want to see how we can define an appropriate function for any reflexive transitive frame which is not tree. Okay. I think it's better to finish this proof and then have a break. Till now we said how we can define the function for trees. Now consider the general case where our frame it's not tree and we may have some cluster. And first I have to define what is the cluster. So yeah. Okay, let's define that. So just a minute. If you have any question till now, you can ask your question. Then I can continue the other parts. Okay, let's define what is the cluster. Let f equal to WR be a reflexive transitive frame. A subset C of W is a cluster if for any W and V in C, we have that W R V and V R W. So cluster is something like this. We have such a picture in our frame. Of any given 2 points, they are related to each other. It's a cluster. Now let me define another notion. Suppose if is in a spore frame By S-form frame, I mean that it's a reflexive and transitive frame. Because we know that S4 is complete with respect to reflexive and transitive frames, we sometimes call such frames as S4 frame. Define an equivalence relation on Fi. We say that W is equivalent to V if and only if W and V belong to the same cluster. Since these points are related to each other, we can see them as a equivalence class. And let F over this relation denote the skeleton that is F over N is the quotient of F by this equivalence relation, and we can define a relation R in W over N as follows. We say that, for example, to class W is related to the class V if and only if there is some W prime in class of W, there exists some V prime in class of V such that W prime is related to V prime. Then we can see that F over this equivalence class form a structure which is like a tree. We call an S4 frame F a quasi tree if F over this equivalence relation is a tree. This construction is not always a tree, but if it's tree, we call our F a quasi tree. Because the time, let's review the construction in here. Okay, I'm going to give a sketch for this part. Let F be a finite tree of clusters. As we say that we can define if we have some reflexive transitive frame, we can define a frame from that which is a tree. So we can assume that F is a tree of clusters. For example, it has some shape like this. Each of them is a cluster. Then we are going to use the same method as we used for tree. We send the contour set to the root cluster and divide it appropriately depending on the size of the cluster. And depending on the branch of the root cluster, send the contour set of the appropriate intervals, module the branching. Again, divide them appropriately depending on the size of the cluster. To do this, we have to use a lemma which says that if X has a countable basis, and every countable subset of X is nowhere dense, then for each natural number there exists disjoint dense and nowhere dense subset A1 to AN of X such that X is equal to the union of AI. And since R is satisfies the conditions of this lemma, we can do this in the appropriate way. And also the contour set satisfies to this lemma. And continue the process, then the result is a map from R to F. So we can show that each finite rooted as 4 frame is a p-morphic, I mean the interior image of an appropriate finite tree of clusters. Combine this with the above to conclude that each finite rooted as 4 frame is an image of R. Now, by using all these results, now I can show that S4 is complete with respect to R. Proof. As I said, suppose that phi is not a theorem of S4. Then there exists a finite rooted S4 frame or model with root R such that in R phi is not true. By above proposition, I mean a proposition which shows that each finite rooted as 4 frame is an interior image of R. There is an onto interior map F from R to W. Define evaluation V prime on R by putting V prime of P is equal to F inverse of V of P. Then F is an interior map from then F is an interior map from model R and V prime to the model F and V. Thus, since it's a surjective map, for the point R where phi is not true, there should be some point in R which the f of that point is equal to R. Thus, there is a point x in R such that in X phi is not true. So it's complete our proof of the completeness of S4 with respect to the real line R. Okay, let us start the second part. Till now, we studied about the c-semantics of modal logic, the semantic which we interpret modal operator diamond as the closure operator. Now we're going to talk about the derivative semantic or d-semantics, where the topological modal operator diamond is interpreted as counter derived-set operator. Let's first review the topological notions. Let X be a topological space and A a subset of X. The point X in X is a limit point of F of A if A has a non-empty intersection with U when we remove X from that. In other words, for any neighborhood U of X, there should be another point which is not equal to X, which is in A and U. We denote the set of all limit points of A by D of A. As an observation, we can easily show that if X and tau is a topological space and A and B are subsets of X, then we have these properties for derivative operator. The set of limit points of empty set is empty. If x is a limit point of a, then x is a limit point of a minus x, because as we said in the definition, there should be some points which is not equal to x in each of its neighborhoods. So it's the same as say that x is in a limit point of a minus x. If a is a subset of b, then d of a is a subset of d of b. D of a is a subset of d of a union of a, and d of a union b is equal to d of a union of d of b. You can prove it easily. I left it as an exercise to you. Okay. As you know and remember from topology, the closure of A is the set of A with all its limit points, which means that A union of D of A. So we expect, and we will see that the derivative operator is more expressive than the closure operator. And if we want to interpret diamond as D of A, and since box is the dual of A, we have to have a notion which is dual of D operator. We call it T of A, and we call it co-derivative. For any A as a subset of X, T of A is X minus D, X minus A. It's the complement of the set of limit points of the complement of A. In other words, X is in T of A if and only if there exists an open neighborhood U of X such that all of U is a subset of A minus X. X can be in A or it cannot be, or it can be not the element of A. Now let's define the satisfaction relation in here. Let M be a topological model. The dissatisfiability of a formula is defined by induction on the complexity of formula. Again, for proposition variables, negation, conjunction, we have the standard definition. For modal operator in here, we say that diamond of phi is true in X if and only if X in D of V of phi. Or in other words, in X, diamond of phi is true if and only for all U where U is a neighborhood of X, U into, the open set. If X is in U, then U intersection with phi minus X is non-empty, or which is equivalent to say that there exists some Y in U where Y is not equal to X and Y satisfies phi. So diamond of phi is true in X if each neighborhood of X contains some points which is not equal to X, and at that point phi is true. So for box operator, we have that box of phi is true in X if and only if there exists some neighborhood of X into such that for all Y in U, if Y is not equal to X in U, and for all Y where Y is in U and Y is not equal to X, phi is true in Y. So for diamond, we have that X is in D of V of phi, And for box, we have that box of y is true in x if and only if x is in T of v of y. The definition of d-validity in model and a space can be defined similar to c-validity, which I mean that a formula phi is valid in a space X if it's true in all points in all models based on that space. So in other words, a formula phi is valid in the space X if and only for any m based on X and for any point X in X, phi is true in X. Neither the axiom for or T is D valid. So why they are not D valid? To show that they are not D valid, it suffices that I provide a counterexample. So let's consider this space. The space which contains 2.0 and 1, and the topology is the trivial topology, which is contains the empty set and the whole set. And let P be true in just 1. Then you can see that in this point, this model, none of the axiom for or T is true. So here S4 cannot be a good logic for topological spaces. But it's easy to see that the axiom K is D-valid in the class of all topological spaces, and also the necessitation rules preserve the D-validity. Again, you can see that P and diamond box of P, then box of P is D-valid. So how we can show that? We want to show that P and box of P, then box of P is D-valid. To show that, we can consider the diamond version of this axiom, which is diamond of P, then P or diamond of P, because I can convert it, add a negation to each of them, and then I can see that this axiom is equal to this axiom, is equivalent to this axiom. So if I want to show that this valid, I have to show that for any model M and for any X in M in X diamond of P, true implies that in X P or diamond of P is true. If diamond of P is true in X, it means that X is in D of P. And from the observation that I mentioned in the previous slides, we have these properties, this property for the D operator, which says that D of any subset is subset of D of A union of A. So D of P is a subset of P union D of P. So if X is in P, which means that P is true in X, or if X is in D of P, means that X is diamond of P is true in X. So this axiom is D-valid, which means that it's valid in all topological spaces. Sometimes to mention that we work with d-semantics or we work with c-semantics, sometimes it's d-valid or it's c-valid, but when it's clear from the context, we just said valid or satisfiable. But if we want to mention in which semantics we work, we say that, for example, it's d-valid or it's c-valid. Now, from the previous session, previous slide, we understand that for finding an appropriate logic for the class of all topological space in this semantic, we have to find another logic. S4 is not good for that. Let's consider the K plus this axiom, which we show that it's D-valid. We call it WK4 because if you remember, 4 is the axiom box P, then box of P, or equivalent is diamond of P, then diamond of P. It's a 4 axiom, but in here we have an addition condition that P and box of P, then box of P. So we call this logic the logic that obtained from adding this axiom to the normal model logic K. We call it WK4. And it's clear that WK4 is weaker than K4 because, as I said, 4 is these axioms and W4 is these X. Before going to prove the soundness and completeness for this logic, let's have a let's compare the WK4 with S4. For any modal formula, I can consider a translation from that formula from S4 to WK4. We define this translation as follows. We assign to each propositional variable P. I mean that the translation of P is P. For conjunction, the translation of bi and psi is the translation of bi and the translation of psi. The translation of negation is the negation of translation. The translation of box phi is the translation of phi and box of the translation of phi. It's clear that why we consider these translation because that in S4 we have that box P, then box of P, but in here we need to have to add this formula to box of P. Let K be any class of topological space and X any topological space in this class, then phi is C-valid in X if and only if the translation of phi is D-valid in X. I think it should be clear because in c-semantic we said that in X, for example, box of phi is true, box of phi is true if and only if there exists some open set U such that X is in U and for all Y in U, Y satisfies phi. In c-semantics, we define the satisfaction of box phi in this way. But in d-semantics, we say that box phi is true in X if and only if there exists some U in tau such that X is in U and for all Y in U where Y is not equal to x, phi is true in y. So in here, in c-semantic, when box of phi is true in x, phi is true in x. But in d-semantics, if box of phi is true in x, it's possible that phi is not true in x, but it has a neighborhood which all its member in all its member phi is true. So the differences between these two semantics is clear in this case. I can set it for box for diamond to diamond of phi is true in c-semantics in x if and only for all u, if x is in u, when there exists some point y in u where phi is true in phi. Y can be equal to x or be any other member. But in d-semantics, diamond of phi is true in point x if and only for any u in top. If u is a neighborhood of x, then there exists some point y in u which is not equal to x, and phi is true in that. The differences between these two semantics is clear from this definition. So by considering that, you can show that by induction of the formula that phi is true in x if and only if the translation of phi is true here, and the translation is defined in this way. Box of phi is true in c-semantics. If box of phi is true, as I said, phi should be true in x and in all of its neighborhood members. But in here, phi may not be true in x. So we have to add phi and box of phi to have the same satisfaction in these semantics. Also, you can prove that phi is a theorem of S4 if and only if the translation of phi is a theorem of WK4. So it's a connection between S4 and WK4. And as we say, WK4 is weaker than S4 and even weaker than K4. K4 is K plus axiom 4. And S4 is K4 plus the axiom XP then P, or equivalent to this P then diamond of P. So again, if we want to prove the soundness and completeness, we are going to use the results from Kripke semantics. For example, you see that in c-semantics, when we want to prove the completeness of S4 for the class of topological space, or even when we want to prove the completeness of S4 with respect to the real line, we use the results from Kripke semantics, where we have that S4 is complete with respect to the class of reflexive and transitive frames. Now we want to show that WK4 is complete with respect to which kinds of Kripke frames. Let F be a Kripke frame. We call F a weakly transitive frame if this condition is true in F for any W, V, and U. If V is accessible from W, U is accessible from V, and W and U are not equal, then we have W R U. Remember the definition of transitivity. In transitivity, we have that for any W, V, and U, if we have W R V and V R W, then we have V R U, then we have W R U. It's a transitivity condition. But in here, we have this property if W and U are not equal. For example, in the case that we have W WR WRV and VRW, which means that we have this shape. In the transitivity, we have that first. I have to have a loop in W because I have WRV and VRW, so I have to conclude that I have WRW when we have transitivity. But in weak transitivity, I can have this condition without having a loop over W. It's proof that WK4 is sound and complete with respect to the class of all weakly transitive frames. And also it's proof that WK4 is complete with respect to finite rooted irreflexive WK4 frames. There is a main point to make our frame irreflexive because, as you said, the main differences between the weakly transitive frames and transitive frame is that in here we may have some conditions without having reflexive point, or we may have the reflexive point. I mean that in weakly transitive frame, I can have both this condition and this condition, and I can't see the differences between those. We can, in all cases, this condition is true. But in transitivity, it's not true in transitivity, but it's true in transitivity. So making a frame irreflexive is a main point in here. Let's say how we can make it irreflexive because it's important. I want to give a proof to show that how I make an irreflexive frame to show the completeness of WK4. We can see the soundness easily by the completeness. Assume that W is a formula which is not a theorem in WK4. I'm going to prove this part. I have the part of the above. We know that there exists a weakly transitive frame F such that phi is not valid in F. Now, F may contain some reflexive points. Now, we replace any reflexive point in F with an irreflexive two-point cluster. Call the new frame G. I mean that, for example, in F we have some point which is in this shape. Then in here I consider the frame which I have make W, for example, W1, W2, and I make it cluster. And for example, in here I have V1, V2, I add V1, V2, and connect them to both of these points. So I duplicate any reflexive point to make a new frame which is irreflexive. Then we can see that F is a bounded morphic image of G. So we have and so in G phi is not valid and G is an irreflexive frame. So we have the completeness of WK4 with respect to the class of irreflexive rooted WK4 frame. By WK4 frame, I mean the frame which is weakly transitive, irreflexive and weakly transitive frame. As we said in c-semantics, any frame F which is reflexive and transitive, is in one-to-one correspondence with Alexandrov spaces. From here to here, we define the offset topology. And to go from this side to this side, we define the specialization order, which says that X is in related to Y if and only if X is in closure of Y. Now we want to see what is the condition in here for weakly transitive frame. So a WK4 frame F, which means the frame F which is weakly transitive, we can consider its reflexive closure, which means that add a loop over each state. We call it F bar. F bar is an S4 frame because it's reflexive and no weakly transitive and reflexivity make our frame transitive too. So it becomes a transitive, reflexive frame, which we call it a spore frame. And then we can consider it as an Alexandrov space by considering the offset topology. Now we can show that if F is a WK4 frame and A is a subset of X, then in F bar, when we see it as an Alexandrov space, the set of limit points of A are on the line inverse of A, where R on the line is obtained by from R by deleting all reflexive arrows. In other words, when I have a weakly transitive frame, when I want to construct a topological space, I'm going to consider the offset topology, but in here, because our frame is not necessarily reflexive, I first make it reflexive and then define it. Or in other words, we can say that for any U, if X is in U, then Rx is a subset of U, where Rx is the set of all Y, where X is related to Y. Again, we have this definition. On the other hand, we know that this space, which is obtained by adding, by considering a bar, is an Alexandrov space. Again, consider that we have a topological space X. In here, we can define our specialization order in this way. I said that we have a topological space X and 2. We define the relation R2 or RD in here. We call it RD. If and only if X is in the D point of Y. Then we can see that X and RD is an irreflexive weak transitive frame. It's clear that why it's irreflexive, because any point cannot be a limit point of itself. So it's clear that when we define our relation in this way, the relation is an irreflexive relation. So again, we can see that we have a one-to-one correspondence between Alexandrov topologies and between Alexandrov topologies, reflexive and transitive relations, and irreflexive and weakly transitive relations. So please pay attention that in here we have reflexive and transitive. In here we have irreflexive and weakly transitive conditions. Okay, I think we can stop for today and continue the other part tomorrow.